Hey guys, my name is Hiraku Murakami with NovaEdge Academics. Today we'll be going over part 2 of topic 8 forces and momentum. So I'm going to start off with momentum here. And momentum is a new quantity that we're evaluating, and it is simply mass times velocity, and it is a vector quantity. Now you're going to see the reason why being a vector quantity is very important in this topic. Now, what is a momentum? Well, I want you to picture a sumo wrestler, right? If a sumo wrestler lunges at you with the same velocity as another normal person, then which one would you feel like you're being pushed against more? Well, you would feel like the momentum is greater with the sumo wrestler. So it is just simply a function of mass times velocity. So the force of that can be expressed as the change in momentum over change in time. Now we're going to talk about this more in detail a bit later, but change in momentum is called impulse. Just keep that in mind, okay? And you might encounter a graph like this, which becomes important later on. I'll explain this a bit later. But for now, keep in mind, momentum is mass times velocity. Now there's a really important concept called conservation of momentum. And what this basically says is the momentum of the system before any collision is the same as the momentum of the system after collision. Okay, you're going to see why it's important. Mathematically speaking, this is what we use to solve any types of problems to predict what the velocity is like after collision. As an example, I have a white billiard ball that's being struck to an 8 ball, right? And I want to see what kind of velocity that black ball will have if I strike it at a certain angle. These are the types of problems we can solve in this topic. Now let's do a practice problem to see what we can get. Okay, and I'll show you how conservation of momentum is at play. Now let me correct this part. This is supposed to be object B. Okay, now pause the video and give this a try. Okay, so the total momentum of the system before colliding is equal to 1.2 times 3.3 plus by 2.1 times by negative 0.6. Now remember that momentum is a vector quantity, so the direction matters. So I need to keep that negative here. So I get the answer 2.364 Newton seconds. Okay, so after we have the ball B, after collision, ball B is moving towards this side with 0.87 meters per second. Okay, the masses do not change, right? So let's put the momentum together. So I'm going to have 1.2 kilograms times it by negative 0.87 plus by 2.1 times it by an unknown velocity. This velocity is the velocity of A. This is what I don't know. So using this, I can solve this because these two values have to be equal to each other. So finally, I'm going to equate this to 2.364 and I can solve for this. So I get that velocity is equal to 1.62 meters per second. So that is the velocity of A after collision. So these are the types of problems we can deal with in momentum problems. Now I'm going to go back and actually solve this cue ball problem. This one is a bit tricky because now it is not one-dimensional. You also have vertical components. So after the ball strikes, okay, we want to predict the velocity of the ball, of the black ball that's going towards this way. So let me label this as V black. This one is V white. Okay, so this side is V white. So I want to figure out the velocity of these two balls. In order for me to do that, I need to divide it into Y and X axis like we've been doing for forces before. So if I divide that, okay, so before collision, my total momentum of the system is simply just the white ball's momentum because a black ball is not moving. Therefore, mass times velocity is 0. So that's simply equal to 0.17 times it by 3. And that is equal to 0.51 Newton seconds. Okay, so the after collision, this needs to be the same. Now remember that this momentum of the ball is only in the horizontal component. What is the momentum in the vertical component? 0. That means the momentum in the vertical component after collision has to also add up to 0. Okay, so let me divide this. The black ball is going to have a velocity VB sine 45 degrees and horizontal component of VB cosine 45 degrees. Let's do the same thing for the white ball. V of white sine 40 degrees v of white cosine 40 degrees. Now here's a negative on this sine value here because it is going downwards. Now, as I said, the momentum in the vertical axis has to add up to 0, which means VB of sine 45 degrees times it by its mass, which is 0.16, has to equal to 0.17 velocity of light sine 40 degrees. Okay, keep this in mind because we're going to use this relationship. Now let's do the horizontal component. The horizontal component is just this plus this. So I get that VB cosine 45, I need to multiply by its mass, 0.16, plus 0.17 V white cosine 40 has to be equal to 0.51. Now here's a problem. I have two unknowns, VW and VB. Well, I can use this expression and plug it in and solve for it. So let's do that. If I simplify VB, okay, numerically speaking, this is equal to 0.966 times VW. Okay, let me plug that in. Okay, so now that we found VW, I can find V black. Now V black is equal to 0.966 times it by 2.13, which is equal to 2.06 meters per second. So that's how I solved for the velocity of the white ball and the black ball after collision in different angles. Okay, this is a bit advanced. It probably might not come up in your exam, but it's good to know how to do this. So here's the thing. We learned in the previous video what the third law of Newton's... Okay, so in the previous lesson, we learned about the Newton's third law of motion, right? Where we talked about every action has an opposite and equal force in reaction, right? This is a concept where birds used to fly, right? But how do rockets navigate itself in space? Because here's the thing. In space, there is no air to push, right? So fish swim by pushing the water and propelling itself forward, right? Birds use the air to propel itself, but spacecrafts, they cannot push any air or particulates in space. So how do they go forward? Well, they just release gas. So at this propeller, it releases gas in this direction with a certain velocity. So every mass of that gas has a certain mass. They also have a velocity. And so collectively, these guys will have a certain momentum, right? Well, that momentum has to also be equal to the momentum of the spacecraft going this way with a certain mass and velocity. And that's how spacecraft navigates itself in the space to propel itself forward. Now, momentum can be classified as elastic, inelastic, and totally inelastic. Now, these are three categorizations, and it's very important in terms of energy. We'll be discussing energy in the next video. Therefore, I cannot go into much detail, but we'll come back to momentum and do also more practice problems that are advanced. Okay, now I'm going to talk about this force is equal to impulse over time of impact. This is a very useful equation to use, and it explains a lot of the natural phenomenon. To explain further, I'm going to use an example. If I fall from a certain distance, okay, and I say I have a mass of 60 kilograms, and at the time of impact, I have 10 meters per second of velocity, obviously my momentum at that point of right before impact is equal to 600 Newton seconds, right? Right after I collide with the floor, what's my momentum? It's actually 0, right? Because my velocity is 0. So my final is equal to 0. So my impulse is actually negative 600. Okay? Now keep this in mind, okay? Well, the time of impact is nanoseconds or milliseconds. It's very small, right? Because boom, I hit the floor, right? So that means force that I experience is very, very high. But let me replace this with a safety net. If I replace this with a safety net, right, my impulse doesn't change. I'm still going from 10 meters per second to 0 meters per second, right? So my impulse does not change. However, the time of impact changes. And when the time of impact increases, what happens? Force decreases. So this explains why I don't hurt my back as much if I have a safety net when I'm falling. And that's where we have this picture. That same concept can be used with gloves in baseball, right? The gloves lets us have a lot more time of impact as it absorbs, right? So that's how it absorbs, right? So that increases the time, therefore decreasing the force exerted by that ball onto the catching person's hand, okay? Hey guys, thanks for watching the video. If you find these really useful, then consider giving us a like and subscribing to our channel. For questions, leave them down below in the comment and we'll try to get back to you. For more academic resources, visit our website at NovaEdgeAcademics.com. We offer one-on-one tutoring service as well as college admission strategy. Let us know what you'd like us to cover next, and we'll see you in the next video.